Hi everyone, welcome to my video series. In this lecture video, I'm going to talk about nuclear physics and radiation. So I like this section because I know a lot of you are medical majors or going to be in the medicine field. So even though I am going to always put my physics spin to things, I want to just point out some things that might be more applicable to you, especially in terms of radiation. So I'll talk about radiation in the context of nuclear physics. So we're going to focus on the nucleus of the atom. We're going to ignore the electrons in this case. And look at some of those properties. So here we go. So we're going to talk about this new force called the strong force. In fact, I know in your homework you're going to calculate the electric force and compare it to the strong force. We're going to talk about radiation types, alpha, beta, and gamma radiation. We're not going to go into half-life, although if you look at the textbook or the reading, you'll see that it goes into great detail with this. I'm not going to go into half-life. I'm going to let chemistry take care of that for you. But there's lots of really interesting information about half-life. We're going to talk about radiation and dosing. So we're going to talk a little bit about the units of dosing and exposure. I'm also going to talk about the environmental effects. So where do you get most of your radiation dosing from, besides, some medical treatment. And then a very tiny brief discussion between fission and fusion. So fission is breaking apart the nucleus, and fusion is making a nucleus. So that's actually all I'm going to really talk about fission and fusion. As always, I can talk about any one of these topics as a series of lecture videos, but as you know, I'm just going to give you some of the morsels and little bits of each of these things. Okay, so why don't we go ahead and start talking about some of this stuff here. So first we're going to talk about nuclear structure. I'm just going to move my tablet because I'm just holding it here. So first we're going to talk about nuclear structure. Now, inside the atom, we have the nucleus. And as you might kind of know already, the nucleus composes of neutrons and protons. So another thing that's really interesting, and it always blows my mind, is I like this drawing because it shows you the atom, but really the atom itself is so empty. It's just so much empty space. There was some great chemistry experiments to kind of prove that that is true. There's lots of empty space. But if the atom is about 10 to negative 10 right here, the nucleus is much smaller. It's 10 to negative 14th. And it's very, 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 very compact and dense. This is incredibly dense. The density here is just remarkable. I used to have the number written down, but I don't have it now. But this is literally the densest thing in the world. It's this nucleus. So we call the nucleons part of the nucleus. So it's basically the the protons and neutrons of this. And this says has a sharp boundary, just meaning that this is really tightly compact right here. And it consists of mostly empty space. So I'm going to go right into notation here. So as we talk about nuclear physics, we kind of like to describe the nucleus in terms of the nucleons and the protons. So we have a couple features. So Z right here is the chemical symbol. Well, it is, but it's the atomic number. So for instance, if we're dealing with potassium, so notice that X is the symbol. It's a chemical symbol right here. K is going to be, for example, the symbol for potassium. Z is the number. So if I were to literally look up on the periodic table, which I did to verify this was true, this would be the number here. This is also the number of protons. So the number of protons and the number, the chemical symbol here, these will never change. In other words, as soon as I change the proton number, then I've actually changed the symbol. So in other words, if I change this to 6 for carbon, then this would have to change too. So this is the number that won't vary. But the top is the number of is actually the nucleons, not the number of neutrons. Ooh, big mistake. Sorry about that. That's why I stopped. Number of nucleons. I wrote the wrong word. Nucleons. I know I spelled that wrong. Here we go. Because this is not the number of neutrons. Oh, I was right. Total number of neutrons. I'm sorry. That's what happens when I think too. Okay, this was right. That was right. We're looking at A. Total number of the nucleus. So the number, I'll put this here, number of nucleons. That's what I meant. Nucleons. Nucleons. I hate spelling this word. I still spelled it wrong, right? Yep. Scratch that. Okay, we're starting over. Okay, yes, so this is A is the total number of nucleons. And what I mean by nucleons is the total number of nucleus. Oh my gosh. Total number of protons. I don't know what I was thinking. Protons, which is the number of nucleons. We're gonna, don't worry, everything works out in the end. Take 3. A is the total number of protons. Oh my gosh. Fix this in post. Oh, goodness. I can't believe I did this 3 times. I'm so sorry. The total number of protons and neutrons. There we go. Which is the number of nucleons. So in other words, this number 40 represents both the protons and the neutrons. So in other words, this is not necessarily double here. And that's a really important fact because that's what's going to come down to radiation, which we'll talk about later. 40 is how many protons and neutrons that you have. So in other words, I can actually figure out the number of neutrons by subtracting the nucleons, the total number, by the protons. So actually, notice that I have 21 neutrons, not 20 or 19 to 19, which is what's it, 38. So that's not always equal amount, and that's important for stability of the nucleus, is to have an uneven amount of protons and neutrons, which I'll talk about a little more. Which I kind of emphasize here. So, summarizing here, A is protons plus neutrons, and that's what A is here, which is also what we call nucleons. Sorry for all those typos, silly me. So talking about what I just kind of mentioned is that you don't have to have the same number of protons and neutrons. I always thought so because of, I don't know, symmetry. But when you don't have the same number of protons and neutrons, we call those isotopes. So here we go. There's 3 different. So notice that, first of all, the bottom number for carbon is 6. That doesn't change because that's the chemical symbol. That defines what the object is. But this top number changes. And what changes is not the number of protons, because there's still 6 protons in each one of these. It's the number of neutrons. So we have carbon 12, 13, and 14. These are known as carbon isotopes. And I'm pretty sure that carbon 14 is what we use to date things because it has a very long half-life. We can actually determine that. Your textbook, if you choose to read it, I actually posted the whole chapter in your notes. Actually goes into carbon dating and all that fun stuff. And like I said, I'm not going to worry about that. I'm just going to kind of gloss over that right now. But just know that you can do that. And that you can have different numbers of protons and neutrons when it comes to atoms. So it's all about actually nuclear stability. So it turns out that if you think about it, protons don't actually want to be next to each other. They're like charges, so they actually want to be repelled. But if you look at it, it's interesting because what happens is you have a bunch of protons together. That's crazy, right? So what's causing those protons to stay together? Well, out of the 4 fundamental forces of physics, this is one of the 4. This is called the strong force. The other 4 are gravitation, electromagnetic, and we have the weak force, which is the radiation, which I'm talking about, and the strong force. Those are the 4 forces of physics. But anyway, we call it the strong force. That's the official name of it because it's the force that counteracts the repulsion from Coulomb's law. So this is the Coulomb electron repulsion. So anytime I use electric force and Coulomb's law, those are all electric forces, electrostatic force. But if you think about it, as the nucleus gets bigger and bigger, you have more electric force, which means that the strong force is going to feel some strain. Now, the properties of the strong force, this is a reference I don't think anybody would get, but this was a 90s TV show I used to watch, and it was Pete and Pete, and the strongest man in the world was Artie. So it's a silly little reference for you for trivia. But anyway, so some of the strong force principles is that the strong force is actually works only at small distances. So in other words, it's about femtometer. Look at this. Look at this, right? You've probably never seen this. F in front of that. Femta is times 10 to the negative 15th. Remember that because you're going to use that number later for your homework. Femtometers. The strong force only works at really strong ranges. So as the nucleus gets bigger, the strong force gets weaker. One way to kind of counteract the counteract the repulsion force, because as you know from electrostatics, is as you add more charge, the force electric will get stronger. So if you have too many protons, it's too strong, so it will overpower the strong force. So what do? You add neutrons. So as the nucleus gets bigger with more protons, what you need to do is counteract it with more neutrons. So this is me just explaining this. So what happens is here you have a pretty good strong force because you only have a couple protons. But then the strong force gets weaker as it gets further and further apart. Did I mention everything here? Yeah, I mean, this is exactly what I said. There's a different way of saying some of the stuff that I said, but that's okay. So just like I said, what happens is you have the stable nucleus and the unstable nucleus, where the nucleus literally falls apart. So the N equals Z line. So in other words, imagine if you have the same number of protons as neutrons. This is what this would be right here. But all of these, what you have here is a better chance for nuclear stability right here. And these are unstable nuclei. So in other words, what you're seeing here, notice at the bottom is number of protons. Notice that we have to increase the number of neutrons at a different rate for stability. This is the line of stability. This is not a stable line. It's showing you what happens if you keep them the same. So this would be a slope of 1, right? 70 to 70. But this is not true. You actually have to increase the number of neutrons to keep it stable. So how do you stabilize a nucleus? You got to add more neutrons. But the heavier the atom is, the more neutrons you need to balance. So there is a tipping point where it doesn't work anymore. Even those heavy elements like 100 protons, you need a ton of neutrons to balance those out. But they're very hard to create because they're just not nuclear. I don't know how to say this. They're not stable. I'll say it like that. So what happens when they're not stable is you start this decay. You get radiation, right? So first of all, you start off. So uranium is one great example because it's not very stable. And what happens is it's going to break down into stable parts. We call this radioactive decay or radiation. Now, we're going to you'll have some homework problems that work with this too. But basically, if you look at what's happening here, this is just like chemistry where you're balancing the top numbers and the bottom numbers. So what happens is that in order for this to become balanced, this is actually a specific type of decay. We'll talk about the 3 types. But this is actually an alpha decay where it basically gives off a helium atom. So notice He. So what happens is notice that 238, the top number, has to equal the top number with these 2 types of radiation, right? So 234 plus 4 gives you 238. So these have to balance. You'll have a homework problem balancing these out. And then the bottom numbers also have to balance. 92. So this will break down into 90 and 2. So notice that these add up to 92. So an unstable nucleus will break down, but we're conserving mass and energy technically when we do this. We'll talk about energy in a moment, but we're conserving mass and energy and charge. Everything is conserved when we break apart. So there's ultimately 3 types of radiation that happens. The alpha radiation is positively charged helium atom, alpha particle, and it's got a +2. So notice that right now this is showing you what happens if you put it in a magnetic field. But in fact, when you put objects in a magnetic field, if they're charged, they start to curve. So basically, I'm not going to go through what the theory about their curves and all this stuff, but just know that positive charges curve, opposite from negative charges, and no charge doesn't curve. So those are the big things, and there's a homework problem on this as well. There's actually more than one type of beta decay, but for now I'm just going to talk about the beta. There's a beta negative and beta positive. The beta negative is basically an electron that kind of pops off, which then gives you a negative charge. You could have beta plus. What happens is that the beta now is positive. It makes a positron. So it keeps the mass of the electron, but changes the charge. So the opposite of an electron is called a positron because it has a positive charge. And then sometimes, like I said, because we have to conserve mass or energy, you have gamma radiation. So if you see, what happens is you'll see no charge. In other words, the radiation will just give off, so it won't deflect in a magnetic field. So alpha, beta, and gamma are the three types of decay that we're going to work with. So just a little bit more detail on all of these. So like I said, here is the alpha decay, which is basically a helium nucleus. So anytime you see helium, that is a signature of your alpha decay. So your book kind of goes through these examples to show you that if you start off here and you have an alpha decay specifically, so that's what the alpha is here. This is called the daughter atom. So in other words, what happens when this breaks down? So notice it's -4 and -2 right here, plus the alpha particle, plus any energy that is involved right here. So in other words, saying that this is like the formula that you use. So let's take a look here. So this is an alpha, this is an example of an alpha decay, because as you can see here, where we have the helium, that's the presence of alpha decay. So this is just a quick balancing equation type of question right here. So an isotope of americum, so this is a 241 AM, so that's a lot of, protons and neutrons in that, is part of the sensing circuit in most circuit detectors. So yes, your circuit detectors, those smoke detectors actually have radioactive decay in them to help detect the smoke. So that decays by emitting an alpha particle. The alpha particle ionizes the surrounding air, creating a current between the two charged plates. Smoke particles entering that region between the plates interrupt the current, which triggers the alarm. So this thing's going off at all times. So when that decays, what is the daughter nucleus? So basically you're doing a chemical reaction, balancing equation here. Of course, my thing timed out. So give it a second to kind of time back in. So like I said, I'm just going to time it back in. So sorry about that. That's what happens when I do this for quite some time. Okay, so here we are. I have it. There we go. So notice that it gives us the top one. It gives us 241. But it doesn't give us this bottom number, which is actually kind of important. So we're going to figure out what the decay is. We know it's going to be a helium alpha decay. So basically we're figuring this out. So first part, if it's not given to you, like this problem was not very nice, right? I'm literally looking it up on the periodic table. I'll tell you that you don't need to do this for any of my assessments, because I'm just going to give you the number, because you could just look it up in the periodic table. So I'm literally, on my other screen here, is getting the periodic table. And americum, it was a americonium, I think that's how you say it, americonium. Americonium has a bottom number of 95, so I'm going to go ahead and write that in. So this is actually 95. So to figure this out, notice what I'm going to do, right? So basically, the bottom number is 95 minus 2, which gives me 93. So I'm looking up 93 on the periodic table, same thing. So if I look up 93 on the periodic table, I should just show you really quick so you can see what I'm doing. So here's my periodic table, right? So here's americonium right here, 95. 92 of that is neptunium. What a cool name, neptunium. NP. So that's what goes there. So NP is 93, that's the daughter one. And then the top, I'd basically do the same thing. 241 minus 4 gives me what? 237. That works out. There we go. And there you have it. So that's the answer to this question. It's going to give you neptunium as the daughter particle, and that's due to the helium alpha decay like that. So when it comes to your homework, you're going to do this. Pay attention to the notation, how to enter this into your homework, because it tells you to do like up, number, down, number, and it tells you how to actually enter this into the homework system. So, but you'll practice some of these based on what kind of, decay that you have. Okay. Beta decay. Put this down for a quick second. So beta decay, you can have a negative or positive, basically. But essentially what you're getting here with beta is an electron. So the electron can either be positive, which is called a positron, or the electron can be negative, which is which is just a typical electron. So if you look at this example up here, here is a beta decay. This would be beta minus because it's negative right here. So like I said, when we do these equations, we're balancing charge, mass, and energy. So notice the algebra here, right? So we have 14 at the top. So there's no nucleus, right? So there's no protons or neutrons. So that's why an electron is a 0 up here. But down here we have a charge. Now notice what happens, right? So we went 6 when we got bigger, right? Well, that's because we have to conserve charge. This is electrically neutral. So what we got to do is we have to take this number, and notice that if we did 7 minus 1, we get 6 on the bottom. So this equals that. So the top numbers equal the bottom numbers. This is still the case when you do this. And that's true whether you have positive or negative decay. And look at this. I mixed them up. Oh, man. I don't notice these things, of course, when I'm doing it. Beta minus, beta plus. There we go. You get the idea. There we go. And same thing. I mean, this is just the formula, if you will, of how to do this. But honestly, what I do is just kind of figure it out as I go through. So here's another type of example, right? So your body contains several radiotype isotopes. 20% of those radiation dose comes from the radioactive decay of these atoms. Most of the dose comes from 1 potassium. So bananas are one example because there's lots of potassium. So potassium, which most commonly decays as a beta minus, what's the daughter? So same thing again. I'm going to go ahead and kind of write out my equation. So 40, okay, and I just happen to know it's 19, but in case you don't remember, I think I had it. There it is. Yes, cool. Look at all that. So where is it? Yep, potassium. There it is, right there. Look at all this cool information here. Anyway, so this is potassium 19. So it's going to decay into the beta minus, right? So that just means an electron. So the electron will be -1 and 0. So the good news is the top has to be 40, so that 40 plus 0 is 40. Now this one has to be increased by 1, so this has to be a 20, because 20 minus 1 is 19. But then I have to look up what element that is. Sorry. Where's my... Here we go. So 20 is calcium. There we go. Oops. I was writing 20. Ca. And there you have it. So in this example, the daughter nucleus is calcium. They're not bad. Actually pretty. I think they're pretty straightforward. I think the hardest part would be looking it up. But like I said, I'm not going to have you do that on your your next exam or assessment. I'll give you the bottom numbers too, just to make things simple. I'm not going to go crazy. Oops, sorry. Okay, so this next one right here is the gamma ray. Let me get this set up right here. Okay, so this is gamma decay. So it's actually no charge at all. It's just energy. So what happens is when these things undergo decay because your nucleus is unstable, sometimes what you get is an atom in the excited state. So that's what the asterisk means, the atom in the excited state, which means actually it's still not stable. So of course, if you remember from chemistry and some of these, past courses. If you're in an excited state, you don't want to be there. You want to be in the lower state or the ground state. So what happens is you get an emission of energy due to the transfer of energy level, and then outputs as pure energy. And because it's a short wavelength, you get a gamma ray. So what happens is that we go, it actually happens twice, but we write it not so much in this form, but notice that we go from this element to, this element is excited, but we have an electron emission plus energy, which we just kind of basically, so notice it goes through a beta decay first and then the gamma ray. So what we do is we summarize it as it goes, this is the ground state, and this is our energy right there. Do we have another thing on this slide? No, I don't. So notice that essentially we go from here to here, but if we're doing a gamma radiation, notice that this number doesn't change, right? Because there's no charge, there's no nucleons. It just goes from unexcited to ground state, and in order to do that, you have to release energy. So that's a gamma decay. So I like this because it's another application. So radiation is used in commercial facilities to sterilize food. One important process is that it kills bugs in bulk. What kind of radiation is the best for this? The answer is gamma, but it goes through Y. So a couple things. So alpha particles can be stopped by paper, so it won't be able to penetrate a thin layer. Penetrate the grain beyond a thin layer of the surface. Beta rays are more penetrating, but still cannot penetrate a few centimeters. Gamma rays, however, are highly penetrating, so be able to go through the deposit, be able to deposit their energy through the entire bulk sample. In fact, electrons are typically used to sterilize thin food products like meat, while gamma rays are used to do bulk products like vegetables on a pallet or wheat. So fun fact, they actually quickly radiate your food before they send it out to just kind of kill that bacteria. It gives it the ability to actually keep its shelf life. I mean, after time, things kind of do get into your food and, they rot. That if you buy strawberries and leave them out, they will look like this. But think about it, if you're getting your fruit from across the country, we don't want it to spoil too quickly, so they actually radiate your food. So a couple other things to know about this is that, I love this note right here, no ionizing radiation can cause damage to material and tissues, but objects irradiated with radiation don't become radioactive. So in other words, you could still eat your strawberries and not worry that they're going to actually be radioactive. Once the gamma rays go through, they're gone, so it doesn't stay there. That's true if you go to the dentist, right? When you get your x-rays, you're not, radioactive during that time. They actually go away, so you're not irradiated when this happens. So this is just a summary of decay. I liked it from your book, so I just put it here. So you can read through this on your own, and this is showing you examples of each, so that if you wanted to go ahead and kind of study these are pretty important. And then the radiation penetration was kind of discussed, but if you notice, most alpha radiation doesn't go through very much. In fact, it gets stopped by paper because it's just really large. And then the electron's a little smaller, so it could go through paper, but not through metal. And then gamma radiation needs something very dense, like lead, to stop it. So those are some penetration of radioactive sources right there. So a little bit about the body and radiation. So radiation, of course, affects your body. You know that. But there's two things that it does specifically that's harmful. First, it drives chemical reactions that won't normally occur. So in other words, because you've given more energy to your atoms, you can actually ionize them, and that actually stops them or triggers ion transfers in cells. So in other words, it causes your cells to behave differently, which of course is not great, especially if you're trying to deliver. I don't know how cells actually transfer these things, but it's for for your synapse and how you receive information that's disturbed by radiation. The other thing that it does is kind of related is that sometimes it just, because it's ionized, it actually cuts and breaks up your DNA. It actually literally physically damages it. So here's an example of DNA being broken by radiation. So fun fact, radiation is when you go tanning. So literally when you go tanning and your skin is all red, some people like, your skin turning colors because of it, but the red is actually showing the damage to your skin. Now your body's really good at repairing that, so that's really nice. But there, of course, is a point where you can't, it's beyond repair, right? Your body can't keep up with the repair. So just know that when you go sun tanning, which is why it's very important that you actually put sunblock on when you go outside, because it literally ionizes your skin cells and causes damage. So I like to talk about sources of radiation because I think there's a lot of confusion out there in terms of where radiation actually comes from. And actually most of your radiation comes from actually natural sources, so the background. Actually the most common source is radon. So there's radon in air. In fact, when you eventually buy houses, it's important that you have a radon test because, of course, you don't want to be exposed to too much radiation. I know I had to have a radon test in our house when I bought it and had to have it treated because of that. But that's the most common source of, go back to this. Most common source of radiation actually comes from natural sources. So where does everything else come from? So yes, medical imaging has some radioactive sources that you use. Your food and water actually has a pretty good, it's not much different than medicine, especially potassium when you eat those bananas. Consumer projects like your smoke detectors, TVs, and monitors. And strangely enough, coal and nuclear plants don't have very much, radiation given off. So that's like one misconception about, about nuclear power. I'll talk a little bit about Chernobyl and about that effect in a moment, but generally fully functional fine power plants don't actually give off a lot of radiation. So we're going to talk about radiation dosing. Now, I know that when you go into your medical field, there's going to be all sorts of dosing terminology and things that you're going to have to learn. So again, I'm just going to give you some physics dosing, talking about it. So I talked about how radiation actually ionizes atoms. So actually to kind of measure the amount of radiation, we talk about measuring the amount of energies that goes into ionization energy. So basically how much ionization energy do you have, and that's how much radiation you received. So we call it a dose of radiation. There's a couple different terminologies. The first one's called a gray, which is a GY for a symbol. But it's defined of how much energy you absorb per kilogram. So essentially what happens is to figure out the gray dosage, we just take the energy and divide it by your mass. I mean, that's the simplest way. I'm going to show you that in a moment. You might see radiation in a term called rad, which is 0.1 gray. So that's just another, kind of like there's like feet and meters. That's kind of what this is. I'll talk about this, but it turns out that the relative biological effectiveness. So in other words, 1 gray of alpha radiation is going to be different than 1 gray of gamma radiation. So we also have to take that into into contribution to it. So in other words, this is kind of like a weighting factor. So which one's more dangerous? We skipped all about binding energy and all this stuff. So I just want you to know that. But some of your homework questions does use a different unit for energy called the mega electron volt, which is actually used a lot when we're describing small energies around the electron level. But just to put it there for you, 1 mega electron volt is 1.6 in negative 13th joules. That's important because when we're figuring out our gray dose, it has to be in joules, in kilograms. It can't be in other units. So major hint, right? So if it's in grams or if it's in millijoules or any of those fun little things, you have to convert out. So here we go. So let me just show you an example. So like I said, I actually write it like this. To find the gray dosage, you're basically going to take your mass and you're going to divide it by your energy. Now, important that your mass must be in kilograms. and your energy must be in joules. That's the important part. So here's an example. A laboratory worker is exposed to 25 millijoules, notice what I did there, of neutron radiation. What's the gray dose? Well, exactly that. So I'm going to take the mass, which is 54. I'm sorry. I don't know why I wrote it. I hope maybe you caught it, but let me write this the right way. The gray dose is energy per mass. My fault. Energy per mass. Sorry about that. So let's try this again. So 25 millijoules. So 25 millijoules. I know that every 1 millijoule, there's 1 times 10 to negative 3 joules, small number. So I'm going to go ahead and convert that. 25 times 1 e to negative 3. .025 joules of energy divided by the mass. So the person's got 54 kilograms. And that's basically what you're going to do. Is just take the energy divided by mass. So 4.63 times 10 to negative 4. Well, this is in gray, so that'll be in gray. If you do this in milligray, I could divide it by 1,000. I'm sorry, multiply by 1,000. Because your computer, your homework question might ask you for certain units. In this case, you have 0.463 milligray. So just know that, this is the answer. Sorry. Right here, but you can express it in different units, so just FYI in that. Okay, yeah, it's just dividing two numbers. It looks a lot more complicated. Don't make it more complicated. So here's that RBE thing that I was talking to you about. I'll just move me out of the way for a quick second. So you notice the different radiation type has different REV. So this is a weighting factor. So if you want to know how much dosage you are, you're going to take your gray value and actually multiply it by this value, which are given. These are given values. You don't have to memorize these. And that's exactly what we have here. So in fact, what we do is we call this dosage equivalent, which is called sieverts. Sievert. That's a fun one. So dose equivalent in sieverts is going to be the dose in grays times your RBE. So we actually could redo that question with this in mind. So let's try it out here. So we have the same worker, notice, of neutron radiation with an RBE of 10. What's the dose in millisieverts? So notice that. So first, I'm going to find my dose in gray. So I'm actually just going to do it again, just to be repetitive. So my dose in gray, so first I got to take this 25 millijoules and convert it into joules. So in 1 millijoule is 1 times 10 to negative 3 joules. I know this is repetitive, but it's good. So that's in joules. So I have to take my energy, which is this. Oops. And then divide it by the mass. There we go. I'm literally doing this again. Just bear with me. So 4.63 times 10 to negative 4 grays. So that's my gray. I got this part. And then I'm just going to multiply by 10. So first of all, in sieverts, it's going to be 4.63 times 10 to negative 3 grays times 10, which gives me 0.00463 sieverts. Okay, now this is technically correct, but it wants it in millisieverts. How fun, right? It doesn't want it in regular. So to do that, 0, 0. The quick way is to actually multiply by 1,000. But I'm going to show you the conversion way. Times in 1 sievert, there's 1,000 millisieverts. 4.63 millisieverts. 4.63 millisieverts. There you go. So that's the answer right there. So I know this is exactly the same as your homework question, so just know that. You'll have different numbers to work with here, and just be careful when converting and looking at what your conversions are. Okay, so we can go crazy with this, right? So here's another example we can walk through. So Jack underwent radiation with a beam of neutrons for his skin cancer. He received a dose equivalent of 18 millisieverts that was absorbed by 25 grams of tissue. The RGB was this much. What absorbed dose radiation did he receive? What was the total energy in the radiation? And then what about Jill? She had a different number. Okay, so the absorbed dose that he received. So notice that basically we have our total sieverts is going to be grays times RVE. So the question is actually asking what is our dose, right? Notice it instead of sieverts, it says absorbed dose. So I can solve that. So that's going to be basically my sieverts divided by my RVE is going to equal to my gray amount, right? First of all, this is in millisieverts, so I have to convert that. So 18 millisieverts times in 1 millisievert, there is 1 times 10 to the negative 3 regular sieverts. So 18. So I get 0.018 sieverts, so I have it in regular sieverts. And then I'm going to go ahead and solve it. So 0.018 sieverts divided by 8 RBE. I'll just write that word in there. It gives me the gray. .00225 grays. That's how much this is part A, is the dosage that I got. So part B asks, what's the energy I got from this? So B, basically I can get it from gray, right? Because the gray is the energy divided by my mass. So I have the grays and I have the mass, so I'm looking for energy. So my gray is 0.0225 grays. It's equal to the energy, which I'll leave as that, divided by my mass. So fun fact, my mass is in grams, so I have to convert to kilograms. And there we go. All right, so now I'm going to solve for energy by multiplying both sides by 0.025. Let's see, 0.025 times 0.025. So the energy I got after multiplying these two values was 6.25 times 10 to negative 5th joules of energy, like that. It's pretty good. It's actually a lot of energy, despite the number. Okay, so that's part B. Suppose Jill also be treating for skin cancer, received the same absorbed dose, but had an electron beam instead. What is her dose equivalent? So basically, I'm changing part A with a different bottom number. So my dose is going to be my sievert value divided by RBE. So my sievert value is the same, but now my RBE, sorry, is a different value. Oops, sorry, I missed the 0. And that's it in grays. It's like that. So there you have it. All right, if you have any questions, as always, let me know. I think that's all my calculations, so good news with that. Move this out of my way too. Okay, so just to give you some perspective on some of these things, right? So first of all, so a fatal dose, so this is not good. So if you see about 10,000, millisieverts, that's a, like I said, a pretty fatal dose. So I went down a total rabbit hole here and was looking up some interesting, facts, because I was watching the HBO special of Chernobyl, and it said that, some of those workers experienced 6,000 millisieverts during their time of that tragic event. So as you know, within a month or so, they were dead, unfortunately, with that. So then I was looking up the exposure of the residents. So they got exposed. I mean, it's not great. Usually, you don't want to go beyond 50, but it's still not a good amount that you actually get. So fun fact, because our magnetic field of Earth protects us a lot from radiation that comes in from space, that astronauts actually experience some greater exposures than that of Earth itself because they're out in space. And then of course when you start feeling any onset radiation poisoning symptoms is about 500. Looking at some other things, so your whole body X-ray scan gives you about 10. The positron emission topography, I believe I said that right, scan is about 7, and then your chest x-rays, mammograms, and dental x-rays. Transatlantic flight, fun fact, that when you go across country, same thing, as you go further into the atmosphere, you have less of it to protect you, so you actually do get exposed to some of that. And that's this one here. So people who use, like pilots, for example, who undergo lots of transatlantic flights will actually get exposed to the radiation from our atmosphere. Crazy, right? Okay, and like I said, I went through a rabbit hole and found all sorts of things. So there's lots of information online. Some conflicting information, right? This said 350 versus, the other things that you... So this is what, radiation sickness. So again, this all depends on, your sources. Another thing I would be pretty interested in is sunburn radiation, right? How much do you experience during sunburn? I didn't get to look at that, but I would be actually pretty interested in seeing that. So what you get mostly, and don't worry about the units here, but the whole point is that most of your environmental radiation comes from radon, which I don't know why it became a shark, because it's clearly not in the ocean or anything, so that's pretty silly. Fun fact, that's the new mascot of radon. Radon is a shark. So it should be, I wonder why it did that. That's funny. Anyway, point is radon. You get some ground cosmic radiation in human tissue, like I said, from potassium. And like I said, the Earth's magnetic field protects us, literally. So this weird drawing is actually the sun and its solar flares, and it gets bounced off by our magnetic field because, like I said earlier, that magnetic fields can actually curve or deflect our charged particles. So that's what the Earth does. Another fun fact, some of them do get trapped in our atmosphere, and that's the effect of aurora borealis. So why we get northern lights comes from the Earth's cosmic rays getting into our atmosphere, and it happens right at the poles specifically, because that's where there's a little gap, or they get charged and they follow the Earth's magnetic field right there. So just a quick little tiny bit of medical applications. So what happens is you can use radiation to help treat things or image. My expertise is not actually great in this area. So once again, I'm just going to talk a little bit about it. But one thing is you can use gamma radiation to target cancer. And the way they do it is quite fascinating. So what they do is they actually use kind of, this looks like, you ever see like a spaghetti colander? It's kind of what it is. They put it on their head. But the way they do that is they allow the gamma radiation to, because you can't really control, like gamma radiation just kind of goes all over the place. But what they do is they put this kind of little colander helmet on, and they allow the gamma radiation to target the tumor or whatever they want, specifically, assuming that it's, of course, not too far away and it's close to the surface and all that fun stuff, to help, kill tumors. Now, if you think about what radiation does, it breaks apart bonds and destroys, the DNA. Part of the tricky part of cancer is that it's mixed with good and bad, tissue. So what happens is that you do run the risk of destroying the good tissue as well as the unhealthy tissue. So that's the problem with cancer and radiation treatments. Just really quick about X-rays versus nuclear imaging. So first of all, X-rays really look at structure. X-rays, of course, work on the principle of being able to go through our body tissue, but not our bones. And that's how we can see our bones, right? And of course, this is good for looking for fractures or anything in your bones. Whereas nuclear imaging is more about bodily tissue and bodily activity. So that's the difference between what you would use when. Generally, and you can see a little bit about the physics behind here, they actually use electronics, they actually accelerate electrons at a specific speed so that they actually give off X-ray light. Is actually what happens. It's pretty interesting. So I'm not going to really focus on X-ray activity. So the positron emission topography actually uses radioactive elements, which is why it's actually not preferred if you can get an MRI, because MRIs doesn't use any radiation. MRIs uses magnetic fields and uses resonance of water molecules in your brain. But this is actually good when it comes down to identifying activity in the brain. Because what happens is that they specifically use an electron and a positron, little particle physics for you. When they come together, they annihilate because they're charges. They're the same charge and the same mass. So this is all the E equals mc squared stuff that you might have heard. When they annihilate, they create energy. And what happens is that when there's lots of active areas in your brain, it actually reacts more with this process. They actually use an isotope of fluorine, and it gives off a positron. So they need a decay to happen to get the annihilation of the electron. And if they happen, they'll go off in opposite directions, and that's why you get some imaging right here when you have more concentrations of area. Or if you're looking for, you can either look for a high concentration of brain activity or no concentration of brain activity. And that's good for Parkinson's disease and Alzheimer's and depression because you're looking for active and inactive areas with that. So so you're using the fluorine isotope. And again, they use it to make, because it actually goes under beta plus decay, so that's the positron that they use for that. So it's pretty interesting stuff. But again, because you're using, you're actually putting radioactive material in your body, in your brain, they don't really like you using it unless you really need it. If something's really affecting your daily life to a point of you need this done. So that's why it's not usually used as often as MRIs. And then to conclude our video, like I said, I'm just going to talk about fission and fusion and then close the case on that. You can actually break apart an atom if you make it unstable. You kind of know that already. So this is what we call fission. We're splitting atoms. When you have fission, you basically not only create new atoms, but you release a ton of energy. In fact, fission is basically a controlled fission or chain reaction is what nuclear power is run on. So if you take a neutron and you bombard it with a uranium, you cause that to undergo a nuclear fission, and you get, I think it's thorium that was called here. But if that thorium does interact with another neutron, that will actually also break apart too. So you get these chain reactions that happen, and they're usually what we call as controlled. So in other words, we know exactly when to put that neutron in and how much, so that you don't produce too much heat, because you release a ton of energy. Now they do this in water. It's crazy. They do this in water, right? So what happens is you heat up water, you make steam, and that turns a turbine. That's all nuclear power is. It's just spinning an object with hot water. And you're making hot water instead of boiling it, right? You need lots of coal to boil water. You know, that's one way power was made, is using coal to boil water, or natural gas to boil water. But the cleanest way and the easiest way is just to break apart atoms. You don't need to, besides getting the atoms, you don't need to do much else. I mean, of course, controlling it. But it's such a clean and efficient way to actually boil water. And once we, really get really good at this, this is the ultimate way of going energy-wise. But anyway, that's fission, is breaking apart atoms like that. And this is how we make, this is nuclear power in a nutshell. Fusion, if you think of fuse, right, you bring together. Fusion is when you take two small atoms and you combine them to a bigger atom. This is what happens in the sun. In fact, this is why the sun glows, because again, when you destroy atoms or make atoms, you release energy. And this is all part of E = mc squared. This is called binding energy. This is all the stuff I kind of ignored in this chapter. But let's go ahead and just talk about it briefly here. Now, this is hard to do because, as you might imagine, you can't take two protons and really just put them together unless you're undergoing so much pressure and you already have, basically, you're slamming into things. So that's what's happening in the sun, is that you have a floating proton and a floating proton, a hydrogen, basically. That's all a proton is hydrogen. You take hydrogen and hydrogen, you smash them together, you make helium, and you release energy. So this is what's happening in the sun. Now the sun has grabbed all that hydrogen because it's under a lot of gravitational pull, and it's literally fusing them together. And then once you get helium, you can get lithium, that's the next element, and then boron, and you keep going. Now there is a limit to how much you can fuse together. The key limit, or the key element, is iron. That's how much a regular star can fuse before it kind of dies. Anything beyond iron is actually made by supernova. What, right? So all elements up to iron, I think it's 26. Let's take a look here since I did have it earlier. Sorry, I'm getting all astronomy into you. So here it is, iron, number 26. This is how much a sun can, or a star can actually fuse together with the amount of energy that you have. Everything else from 27 on, it's all star stuff, star explosions. So I don't have my ring on, but my ring, gold, is made from an exploding star. What? That's crazy. Isn't that awesome? That's awesome. I hope you find that's awesome. Like the silver and my gold of my, jewelry, tin cans, lead, radon, xenon. Let's see what else is really krypton, tungsten. I mean, literally all this franconium. Fun stuff here. It's all made from explosion of stars. Fun little fact for you. We're made from star stuff. Isn't that great? Of course it is. I think that's a great note to end on. I'm not going to do this because it's, a couple minutes. But I highly recommend you watch this video right here because it really just summarizes everything that I talked about really nicely in a way better job than I could have done. But I love this. So we don't talk about binding energy, but it does talk about the fission and strong nuclear force and how it works. So it's a great summary video. So I would have shown this in class because of the importance of this video. But I'll let you do it for this case right here. So, like I talked about, we talked about the nucleus of an atom and how it becomes unstable. First of all, it's stable because the strong force, but once the atom gets big, the strong force gets too weak because it only works at small scales. So once we get too big, the atom becomes unstable. So we stabilize atoms to kind of counteract their repulsion force by adding neutrons, but even so, as you get bigger, the strong force weakens. And then we get nuclear and radioactive decay. So we've got the 3 types of decay that we talked about, the alpha, beta, and the gamma. We talked about sources of radiation, some dosing, and how to kind of understand that. Some brief ideas about the medical equipment that you'll be using, and a little bit about fusion and fission here. All nuclear physics. So that ends my video on nuclear physics. And remember, we're all made from star stuff. Have a good one.